Hello, we're students of MECH533 Subsonic Aerodynamics, and we are giving a presentation of the project that we did for the course. I believe we're group number 6. My name is Sean Main.
I'm Nedić.
Hi, I'm Ravi.
And I'm Clement Bas.
So quickly the design targets. So we have to have a static thrust of 0.2 Newton at 5,000 RPM, maximum efficiency at 9,000 RPM with a wind speed of 5 meters per second. We have to have the minimum weight possible and only use the 4 digits major profile.
Okay, so by now we have seen what are the test requirements. So there were certain values that were said that we had to achieve. So with that in mind, we started looking at propellers, and a propeller is nothing but 2 or more sections of airfoil which is rotating, and the design of it is very similar to that of a wing design, which is nothing but a subsonic airfoil. So here we have a diagram of the airfoil. Let's say this is the airfoil and this was the hub of the propeller, and you have the induced airflow, which is nothing but the total the true airspeed, which is the free stream velocity coming in front of you, and the speed of the propeller with which it is rotating. So induced airflow is nothing but the summation of the two, and that would cause a relative wind velocity, which is explained better here. So the flow angle, the pitch angle, is basically a summation of flow angle and your angle of attack. And now your flow angle is coming basically from a downwash. And your angle of attack is set by knowing the maximum L by D ratio. And from aerodynamics, we know that it is a certain positive value. And that positive value was found by our calculations. So we referred this book called The Performance of a Light Aircraft by John T. Lowry, and we had certain calculations. We found the performance of around 10 different airfoils using X-foil, and then we chose our best according to the efficiency. Some of the parameters that were very important in calculation was the J, which is the advancing ratio, which is nothing but the free stream velocity divided by your N, which is your rotating speed in RPM, in RPS, rotation per second, and the diameter of propeller. So for every section, the value of J was fixed, which was around 2.5, and so we were constrained to getting the maximum efficiency.
So basically, the calculation is done on every section of the airport, and we calculate for each section the thrust coefficient and the pressure coefficient, power coefficient. And for each section, we had to implement an angle of attack and a chord. And we want maximum efficiency at J equals 0.25. We thought that we had to have an angle of attack for which the LOD ratio was the highest. And the chord was set by adapting a formula for another propeller that was the McGill DTM 7557. That was an example in the book. So basically, what the Excel sheet does, it calculates the pitch angle so that the advance ratio calculated matched the desired advance ratio. And then after many runs, we found out that the best profile was the MECH 004. And we have calculated efficiency of 0.415.
Once we have the NACA profile, we're going to draw the part on the CATIA design. So there's 3 main points that's important for it: is the joint from the propeller to the hub and the end of the propeller. The calculations only give us the chords from 50% of span to 95% of span. To get the tip of the propeller, we decided to have a taper ratio of 1/3. And to connect the propeller to the hub, we decided to do an extrapolation of the calculations we had so that we can join the propeller to the hub. Once we had the CAD design, we wanted to see if the propeller would resist the efforts that were going to be given to it during the test flights. So we decided to do a static analysis of the structure. We saw that it would resist all of its efforts, so we decided to reduce the weight of the propeller by hollowing out the hub thus reducing by half the weight.
So we started testing. Yeah, we got our model printed. The motor was in E-Flight ELM 1809 and was set to rotate on a clockwise direction. So we tested on a static level where there was no free stream at 5,000 RPM. And then we started giving a free stream velocity of 5 meters per second, and we changed our RPM from going from 5 to 6 to 7 to 8, 9, 10 up to 12,000 RPM. The thrust and torque were obtained and were tabulated.
So during the conduction of the test, the finishing of the surface was a little rougher than we thought. So when we broke it up, you still have to see a little bumps near the trailing and the leading edge. Another thing was that the direction of the rotation was different than what we thought. It was actually counterclockwise, so the twist angle of the propeller is actually in the opposite direction, so all of our test data came back negative, but the values are still valid. It's just instead of propelling, we're propelling the other way. In the construction of the hub itself, we could have used a flat plate like the book suggested, but we think a more pointier or smooth gradual change at the tip of the hub would help the aerodynamic, the floats that comes onto the blade from the center to the propeller. For the effect of Reynolds number on propeller performance, in general, for Reynolds number below 500,000, a Reynolds number a decrease would lead to an increase in drag coefficient and decrease in lift coefficient. So if lift coefficient decreases, then a direct effect is that the power coefficient and thrust coefficient would also decrease. A drag coefficient increase, then there's an increase in power coefficient, but a decrease in thrust coefficient. This behavior can be just explained by the boundary layer condition. So as we know from class that if the low Reynolds number occurs, then there's less inertia in the flow. There would be separation bubbles that can form just above the surface. So the separation bubble causes an increase in drag and a decrease in lift. So with the test motor spinning at 5,000 RPM, which is relatively high for a small propeller, this would actually enable the larger portion of the propeller to experience a higher Reynolds number. But the center hub is unavoidable for low Reynolds number. So the comparison between the center hub and, let's say, 80% of the propeller length outwards, the difference is actually quite significant. So in higher Reynolds number, this implies that there's low drag coefficient and higher lift coefficient. Lowering the drag coefficient and raising the lift coefficient both have a positive effect on thrust coefficient, which is an increase in thrust coefficient. But the other way around is not true. Lowering the drag coefficient raises a decrease, causes a decrease in power coefficient, but a rising lift coefficient would cause an increase in power coefficient. So the effect on thrust coefficient and power coefficient is the opposite.
Consider the effect of J on our efficiency. We have a MATLAB code that calculates that calculates the efficiency for a given advance ratio, still following the book by John Tillery. Instead of varying the pitch angle, the angle of attack varies to find the required advance ratio. And then by doing that, we found that the maximum efficiency is reached at an advance ratio of 0.35 for an efficiency of 0.4655. And that corresponds to rotation of 6,600 RPM.
Just to go over the test results a little bit, what we designed, target was around 0.25 advance ratio. We were expecting close to the maximum efficiency of 0.4655. In reality, the region of J, where we expected the maximum efficiency to occur, around 0.25, was 0.41, so that's close to what we expected. But the unexpected part was that we expected the efficiency to drop, but
the test result came back with something that just went higher. So I think maybe the probable cause for that was that our hub was much larger than everyone else. We weren't able to screw on the hub securely to the motor.
In conclusion, we noticed that the hub might not be the most effective we wanted it to be. So we could choose to make changes in our hub to make it lighter. We also made the mistake of putting the hub on the wrong side, and well, the results are all backwards, all negative, and the hub also prevented us from securing the propeller correctly onto the shaft, so we might want to rework on that.
Yeah.
We did the best of the 4-digit, but we noticed that 4-digit NACAs might not be the best for propellers, so we might want to look into either 5-digit profiles or into other types of profile other than NACA profiles. Thank you for watching.
Thank you for watching.